A 70-meter diameter parabolic antenna rests beneath the Madrid night sky, pointed towards an empty region between the constellations. What does a machine from the 70s still listen for in the interstellar dark? Let's trace the signal of the Voyager 1 probe beyond the frontier of our solar system. The antenna in Spain is part of NASA's Deep Space Network, a structure designed to capture whispers in the abyss. The signal it attempts to focus is nothing more than an invisible trace emitted by a 22-watt radio. It's the same power used by a refrigerator light bulb. This beam of energy travels through space at 300,000 kilometers per second. Still, it takes 22.5 hours to cross the distance between the transmitter and receivers on Earth. What reaches the antennas is a tiny fraction of a billionth of a watt. The computers isolate this background noise, filter out radiation from other stars, and translate the pulse into a sequence of zeros and ones traveling at the speed of light. The binary code, the result of this translation into zeros and ones traveling at the speed of light, was born from technology conceived in the late 60s and launched in 1900. Voyager 1 departed Earth mounted on a Titan rocket carrying magnetic tape recorders and computers with less memory than a modern remote control. Its initial objective was clear and limited. The probe was meant to fly by Jupiter and Saturn, photograph their moons, analyze their rings, and conclude its primary mission in the early 80s. The instruments mapped gas storms and volcanoes on distant moons, fulfilling the original contract with science. But the orbital mechanics had a secondary effect. Saturn's gravity acted like a slingshot, accelerating the craft and altering its trajectory out of the planet's elliptical plane. The probe was flung upward and away on a one-way journey towards the edge of our sun's magnetic bubble. Engineers kept the essential systems powered as the sunlight on the craft's panels grew progressively weaker until it reached a region where our sun's influence finally fades. In this region, where the sun's influence wanes, lies a physical boundary called the heliopause. The solar wind, a constant flow of charged particles bathing all the planets, pushes against the interstellar medium, creating a protective cavity around our system. In August of 2012, Voyager 1's sensors registered a drastic change in the environment. The count of solar particles plummeted abruptly. Simultaneously, the detectors pointed to a sudden increase in galactic cosmic rays, high-energy particles originating from distant supernovae. The probe had crossed the heliopause. For the first time in history, an object built by human hands was navigating the ocean between the stars. The expectation was that the interstellar medium would be a clean vacuum, devoid of activity beyond the occasional passage of distant radiation. The density of the plasma around the craft dropped to minimal levels. With the cameras already switched off to conserve energy generated by the plutonium thermoelectric generators, the onboard instruments prepared for absolute silence. But the instruments did not find silence. The probe's plasma wave subsystem, designed with 10-meter-long antennas, continued to register vibrations in the local magnetic field. What if the space between the stars has its own continuous physical signature? The data revealed that the interstellar medium is not an inert void. It's an extremely thin soup of ionized gas, and this gas is constantly agitated. The antennas picked up a persistent hum, a low continuous frequency of plasma waves resonating in deep space. It's not sound in the atmospheric sense, but density waves vibrating in the interstellar gas. The probe discovered that space out there has a texture, a dynamic of its own dictated by neighboring stars and collisions of cosmic dust clouds. Each variation in this hum helps scientists map the density of unexplored space. But the ability to translate these waves into usable data depends on the fragility of hardware nearly 5 decades old. This nearly 5-decade-old hardware rests inside an aluminum chassis subjected to extreme temperatures. In November of 2023, the flow of discoveries ceased. Voyager 1 began sending a repetitive and indecipherable data pattern. Telemetry indicated that the probe was receiving and executing commands, but the flight data system, the computer responsible for packaging scientific information, had failed. The distance was 24 billion kilometers. A team of engineers had to diagnose the problem by analyzing paper manuals from the 70s. They discovered that a single memory chip had corrupted, possibly struck by a high-energy cosmic ray or simply by the wear of 47 years in space. Without physical access, the only solution was to rewrite the flight computer's code. The code needed to be divided and reallocated into different parts of the probe's functional memory. In April 2024, the correction command was sent via the Deep Space Network. The team waited for 45 hours, the exact round-trip time for the signal. When the response finally reached the antenna in Madrid, the monitors on Earth once again displayed accurate readings. With the restoration of accurate readings, what we came to seek is finally revealed. The machine from the 70s listens to the slow breath of the galaxy. It's not just floating in the dark, it's measuring the pressure of the interstellar medium against our solar bubble and recording the impact of stellar winds from suns we'll never see up close. The data it still sends proves that deep space has weather, currents, and density. Voyager 1 transformed the absolute void into a tangible environment, a place we can now observe through the sensors of an aging probe. In our next episode, we will investigate Hubble, what 35 years in space revealed about the universe. A golden copper disk advances in silence, surrounded only by the radiation of stars that no longer exist.